Is to welcome Beth Wingate, who I think you probably all know.
So as the title suggests, I'm going to be the beginning of my talk is going to be about the new computing architectures, which I've never before been interested in, and I believe that I'm still not interested in to some extent, but it's worth discussing here, and I'm speaking about it. I'm telling you everything I know, so questions that you may have I may not be able to answer, but I'm interested in having a discussion about the issues raised by these architectures at this meeting, because I think if the people in this room don't do something about this, no one will. So I am then going to go on and say how the change in these architectures have inspired me and others, my collaborators down here, to look at alternative ways of time splitting, but that's just the tip of the iceberg. I'm looking at the time splitting issues in a way that's more amenable to successfully or more efficiently working with these new architectures, but I think there are numerous things to be done. So this is just a beginning, and I'm going to explain some of the concepts that underpin what we're doing, but Terry Hout, who is a postdoc working with me, will be talking about the details of what we've done so far at the PDEs on the Sphere meeting in a few weeks. So this talk is more about introducing ideas that I wish to have discussions with you all while I'm here. So the first thing I'm going to do is talk about, I say terminology, but it's really what does this mean, this change from petascale to exascale. And I'm going to try to convince you that this is an important moment for computing, so important that I became interested. And then I'm going to discuss this alternative idea for time stepping. Okay, so I've been influenced by the US Department of Energy, and this is where all of this knowledge comes from. So it could be that I've been brainwashed. But okay, so exascale really means 1,000 times more than petascale, and I've heard the exascale term used as extreme scale, and I think it really is, because the problem is that the major design constraint for new architectures is power now. It isn't, about the chip anymore. It isn't, the chip design is still important, but the Moore's law is about to hit a plateau. And I've heard this coming for a long time, and I didn't really pay any attention, but here's some perspective, about how things have changed since 1946. The ENIAC, 1,000 flops per second. And this just is what people are expecting in 2018 there's a lot of zeros, flops per second. And this is more than we can use, effectively at this current moment. So here's the problem. So this red line is how the system power in megawatts will change with usual construction types for architectures. You can see by 2025, 200 megawatts. Now this can be compared to a city of 80,000 people, which uses 45 megawatts per year, and so this would be 200 megawatts per exascale kind of flop. So this is too much. So the goal is to get it down to about 20, which is still a lot, but this is the serious nature of this computing problem, which is, you're used to waiting, you just wait a little while and you get a new laptop and it goes faster, or your university or laboratory buys you a new computer and you know nothing about what's under it. You're just given the compiler instructions. You learn a new version of MPI and off you go. Well, that's about to change. And this is a figure I barely understand, but this is the power along this axis, and this is the type of operation that's going on, and this light blue line is what's happening now. So you can see that the cost of the flops is going to go down, but up here, these are internode data transfer kinds of issues. So the idea is that you have to do more flops and less data transfer. And so these are the two main concepts right here that I know about. And there are various flavors of combinations of these things, but there's the homogeneous many-core option, which are low-power processors. But to reach the exascale, they will cover a lot of square footage. So if you think you're doing an elliptic solve on something like this, where all the processes are connected to each other, you know, you're going to be waiting a while for that to execute, you know, sort of bounded by the speed of light. So then there's the heterogeneous computing style, and this is what I know more about, and this is what I'm going to talk about because this is the kind of machine Los Alamos has, but I by no means know which is the better strategy. And from what I can tell, public opinion says these are called swim lanes in the Department of Energy. They tried to remove every occurrence of this because it's DOE jargon, but that they will eventually merge and they will eventually become some optimal combination of each other. So whichever way wins the day, you know, maybe the problem is we're going to have to be even more local than we are now. And this kind of reminds me of many years ago, the switch from vector machines to parallel machines a lot. There's people who probably know more about this than me, but you know, I feel the same resistance, only now it's in my colleagues, not the generation earlier, right? There's a resistance, but you know, we were sort of forced to go from vector processors to parallel, and we learned about domain decomposition. And we're going to be forced to do this too, because nobody's going to build for us a 200 megawatt per exaflop machine. So this is the old paradigm that I'm used to. You know, when I showed up at NCAR as a postdoc, there was a new computer. And the kinds of things that happened was that the Fortran compiler wasn't very efficient, so Rich Loft called the computing company and said, fix the Fortran compiler or come and take your computer back, right? So people like us do this. We have a new algorithm, we port it to the architecture, and we go round and round like this. So we have a lot of creativity here, and we've made a lot of progress here, but I think that's all about to change. And this is what I'm going to be describing in the second half of my talk, is my experience with this. So that, in fact, you have this giant loop, including architecture people. So I think of these people, and these people over here as the people who didn't want to make my Fortran compiler go fast. But this is changing the algorithms here and incorporating the data in the visualization. And a lot of this is because these computers have more of a design element than they used to. So I'm going to tell you a story. So I'm driving back from a meeting in Tennessee with a computer scientist and a hardware scientist. You know, this is one of these bar stories. 3 scientists walk into a bar. 3 scientists are driving to the airport from a meeting, and one of these guys is from NVIDIA, and I am saying, I don't believe you. I don't believe that you want to work with me on making a new architecture. Why should I waste my time with this? And he says to me, think of these new architectures as Mr. Potato Head, which is you can move his nose to the top of his head, or you can move his ears where his eyes are. And this might not seem that interesting. Actually, I said to my friend Pat, afterwards I said, wow, look at this guy using metaphors I can understand. And he said, Beth, that guy is a salesman. I was like, oh, okay. But anyway, and I'm going to talk about this more in just a few minutes. What this effectively means is, for example, in the heterogeneous architecture with the GPU, there's a very particular kind of memory, and if you can put your data in this memory, you get a filter for free. And they can design chips to do very specific things super fast. You know, so one of the things that's being done at Los Alamos now is people have recoded things so that you put the vertical column physics onto the GPU or the cell processor or whatever it is, and you do like an elliptic solve just down, you know, a tridiagonal sort of thing. So it's possible to design a chip that does that in particular, right? So this is interesting, and So I've been considering what is the idea of a climate scale ocean model on one of these new architectures. And we have a new machine at Los Alamos that has these NVIDIA Tesla GPUs, which, you know, have double precision floating point operations and things like that. And I've learned how to program in CUDA, which, and then OpenCL, which this is the kind of language you use to operate from the CPU to the GPU. And so this is what these things look like at the moment. So you have a CPU with this chipset and memory, and then you have a device like a GPU that has its own memory. And these two things are presently connected by this PCI Express bus, but it's very slow. It's the slow boat to China bus. So you have to, I mean, this worked just fine for the original application of these GPUs, which were, by the way, constructed in order to sort of pay attention to the fact that we were reaching Moore's law, the limit of Moore's law. So they started making GPUs to do the video part of your laptop or whatever, and they would just pump data up the bus, and it would do things to your screen and then just get rid of it because you were pumping things in. You didn't have to bring things back. Now, what's happened recently is that eventually this bus may be shared memory, which is more interesting for us. But right now, at least the machine we have at Los Alamos just has a PCI Express bus here. So how we move data from here to here, how we sync things up matters. And the key issue about making this work well is seriously stupid parallel. I mean, it has to parallelize really well and in a very particular way. And I give some examples here of how you have to start thinking about data transfer and things like that. Kathy Yellick said, isn't scientific computing hard enough without us having to know all this? And I was like, well, if I can know all this, lots of people can. So anyway, here's what I mean. This statement here is data independent. A equals 2 pi plus x, b equals y times z. And this is data dependent, where you can see you compute A here, but you use A here. This you cannot do on a GPU without shutting it down. It has a very lightweight operating system. You know, we're used to having these very clever operating systems, you know, that will break up our loops for us and keep track of how much things are in cache sometime. I mean, the GPUs, to take advantage of them and to make things especially local, you have to start thinking about how to make things like this, instructions like this, processes like this, where you can do this kind of thing. And I'm giving you an example here of what a C program would look like. You know, you'd have logic to execute maybe your favorite finite volume method here. Then you'd ship data, you know, this would begin, and then you would ship memory to the GPU. You would do the column physics. This is the instruction on how the GPU should use its memory right in here. And this is where you have to do the work. Normally, for us, a compiler would do this. And then you would have a call to ship the memory back, and then you would make all the data global. And this, for example, is how you would have an ID for every element that's related to blocks and so forth. So this is how you keep track of all the instructions that are going on. Is there something like this? And one thing I didn't put in the slide, which I need to, is another really powerful part of this GPU-CPU thing is through asynchronous control. And in the CUDA class I took, I was with other applied mathematicians who do image processing. And there was this moment at the very end where we were learning all kinds of things about the GPUs and its relationship to the CPU, where the whole point was to design an algorithm that would do asynchronous communication between the CPU and the GPU. And which means you don't issue an instruction to wait until everything is done. That slows down the efficiency. What you want to do is let everything finish in its own good time. And you have some control over that by how you issue the instruction to the GPU. So you can imagine we could do things like understanding how data propagates along characteristics. We can set up GPUs so that we don't have to make everything sync up. We design the data flow so that it does, which I don't want to be the one to do that. But so this is this asynchronous data threads. There's already plenty of existing FFTs, sparse matrix solvers, and things like that to try out. But we need some good programming models to optimize. But here's the thing where I'm trying to convince you guys to be very interested in this, which is the computer scientists sort of have this idea that if they just give us programming models, like here's how you compute the divergence, that's good enough. We don't need to know what's going on with these architectures. But since the architecture people are actually willing to work with us and to change the architectures compared to what we're interested in, and they're interested in climate and related subjects, I think it's a mistake to let the programming models people who are much better at understanding interfaces with architectures than how our problems go onto the computer. It's a mistake to just let them tell us what to do. Because if we don't figure out how to make our algorithms more local, we are going to get maybe a factor of 2. I mean, I have anecdotal. I don't have it on here. Maybe I was going to talk about it later. But I'm sure everyone in this room has anecdotal evidence of how something ported onto an architecture. There's so Oak Ridge ported Mark Taylor's 3D, your atmosphere, CAM, right? And took 2 years to get a factor of 2. So even with spectral elements, which has this feature of gratuitous multiads, and which you expect to have locality, a factor of 2. So what does that mean for us if we get a factor of 2 now, and we never get the architecture to give us more than that? We have to do the actual parallelization in a different way. We have to do the algorithms different, because this is going to be a plateau for our resolution, how much we can compute if we don't participate in this. So here's some more general remarks.
Beth, I think that factor 2 is that's comparing using the GPU and not using the GPU.
Right.
If you compare, you could also compare using the GPU or if you had put another processor in the socket instead of the GPU, and then it's only like 1.5.
Still not too impressive. Not impressive. So the reason it's impressive, so for example, people who use Monte Carlo have gotten factors of speed up of 1,000. They figured, things that are stupidly data parallel, and they have figured out to do with the long-range particle interactions, and they've gotten enormous speed ups. And they are set up to scale with all the new architectures that come out afterward. So
we don't leave people the wrong impression.
Yeah.
That's the CAM model. It has like 500,000 lines of code. They started with a few computationally intensive kernels and put them on the GPU.
Right, yeah.
So they have maybe many more years of work to go.
Yes, I think that's possibly true. And in fact, that.
Two-factor of 4?
Yeah.
So I think
But
individual kernels run, 100 times faster than they did before, but the
what
overhead.
do you write it in C? Everything converted into C? Like
It's Fortran and CUDA.
CUDA Fortran.
yeah, but I mean, the whole point of me introducing the subject this way is to try to convince you guys that a deeper examination of our algorithms is required right now if we want to get benefits like the astrophysicists, for example. And if we want our applications to start scaling, we've got time. This isn't a doomsday talk like tomorrow it's all over. But as you guys well know, it takes a good 10 years for an algorithm to become something that stands up in a climate model, for example. So I think we can't. I'm introducing the subject this way because I think there's more to be gained by a deeper exploration of the algorithms that we're using. Domain decomposition, it was great going from vector to parallel, but maybe we need something different now, not just domain decomposition, maybe space-time decomposition, I don't know. So I just say this here, and so why on earth should we spend our time on this? Because if we work with the architecture people and the computer science people on purpose, we're going to get a vote in what the new kinds of architectures look like. And if we don't, it's going to be the things that scale really well. So it's going to be things that do well for the astrophysics problems. They're not just exotic ideas developed by esoteric chip designers, which is how I perceived this before. This is because of the power limitations. This is the future. So I kind of think that we should all try to work with these people and make sort of teams of people to see if we can think of alternative ways of constructing our algorithms. So and why leave the future of scientific computing in the hands of the gamers? All right. So part 2 is partly because of all this, I was trying to think of, is there anything I could do to try to make better use of these architectures? And so I have an idea of, I don't know if it's a new approach, it's an alternative approach for time stepping that we don't commonly use, but there's a lot understood about it mathematically. So these are my collaborators, Terry Hout, who is an applied mathematician. He's a postdoc working with us. Phil Jones, who many of you know. Pat McCormick, who is a computer scientist. He is the link to the architecture people. You remember, the only thing I understood this architecture guy said was about Mr. Potato Head. Jared Whitehead, and myself. So to put it in perspective, I wanted to remind everybody of the favorite ways of time stepping an ocean model, or at least an IPCC class ocean model right now. There's 2 favorites, and they vary in detail, but the concepts are put in 2 camps. There's this split semi-implicit, where you take an implicit step, a big implicit step on the fast dynamics, and it meets up with the time step of the slow dynamics. And the fast and slow in the ocean context is understood to be that there is a depth integrated fast part, and it is faster than the dynamics in the baroclinic part. And then there's the split explicit technique, where you take many small time steps for the fast dynamics and you meet up with the slower baroclinic stuff at the end. So this time step and this time step, you know, are probably approximately the same. It's what you're doing for the fast, this two-dimensional mode, this two-dimensional dynamics. That's the game. And so now I'm going to take you through a look at the shallow water equations. We're all really familiar with these equations, so this is what they look like in their dimensional form. And then I just non-dimensionalize this. I'm not going to give you the details of how I did it. You can do it numerous ways. But I did it in the style of Emba and Maida with a small parameter here, which has to do with the Rossby and Froude number. And this is to easily see how to get to the QG limit. So in terms of, there's two known slow limits of these equations. One is the QG limit. The other is the case when the sea surface flattens out completely and you get the 2D Euler equations, or Navier-Stokes, whatever you want to call it. Anyway, what you can see here, here's the 1 over epsilon. So this thing is getting small. Epsilon gets small, and then the flow is dominated by this is geostrophic balance, and this will become horizontal divergence is 0. And so you can use an abstract form, you know, say there's a v vector that includes all of these, and you can put the equations in this form, and again you can see that the epsilon, so epsilon is like Rossby number, and it's the faster the rotation or the stronger the stratification, you can think of the more important this term is going to become. And this is often associated with the method of multiple scales, so you expand the local time derivative into a fast and slow part, and you can see that the dynamics break up into this linear dynamics for the fast part and everything else. So all of the fast dynamics in the shallow water equations come from the linear dynamics. And so this, yeah, that's right. So this begs the following decomposition, which is you make a transformation of variables. You say W is a linear propagator, so this is a matrix exponential on V, which is your vector. And this is just the solution to the linear problem. And you can substitute this directly into the shallow water equations, and you find an equation like this, which is everything else. It includes the nonlinear terms, but you have these linear propagators in here too. So you've split the problem into its linear piece and everything else. And maybe you can see where I'm going with this is that it would be a two-step process, and that you would solve the linear piece really fast on a GPU, and then you would use some other method to advance this using more of the CPU memory. Now that all these can cross each other, this is just a concept at the current moment. So here's a picture of what I think it looks like. You know, you advance this here, and you advance this here, and I think the concept I'm thinking of here is that you would use heterogeneous numerical methods. And in climate models, we already do this. We use a different method for the atmosphere, we use a different method for the ocean, different methods for the ice, and they're connected through interfaces. But I'm proposing that we think of doing it in this context too. So I'm going to be, yes, Alistair?
So the presumption here is that linear propagator is local. That's why you're justifying it.
So I'm not justifying it that way at all. How I'm justifying it right now is splitting it into two pieces. That's all.
But the original diagram we showed of how we do it now, it is also split. You know, we do an explicit fast part and the
That's
slow
right.
part.
That's right. So I'm splitting. So I say that the fast shallow water equations actually have fast and slow things in them as well. And so even though it's faster than the baroclinic part, it still has a fast-slow decomposition by itself. So this is the fast dynamics of the fast system. So that is the assumption which I'm going on. And in fact, I will say a little bit more about this too, because our ocean doesn't sit at a place where the parameter is small. It wanders in and out of parameter space. Sometimes the parameter isn't small, sometimes it is. And so even though I'm viewing this as the fast dynamics, really I have to view it as the linear dynamics, and I have to solve it accurately whether or not it's the fast or slow piece. It's the linear part of the problem. So,
Is that not also the part of the problem that communicates like crazy because it's fast?
no, okay, so you've just set yourself up to be interested in Terry Hout's talk. All right. So the method we're using, well, I'm getting ahead of myself. So
Okay, I'll shut up and I'll wait for you to get there.
yeah. All right, so here's my remarks about the splitting. Vast body of literature about the top of splitting the problem into fast and slow. And I don't mean barotropic and baroclinic, I mean the fast part of the shallow water equations. Let's just talk about those, the fast and slow in the shallow water equations themselves. And these are the standard text, and probably everybody knows these books. And there's been a great deal of progress for multiscale methods in PDEs. For example, the heterogeneous multiscale method, notably Wynand-E, Jorn, Enquist, and those guys, but many others have made contributions to this. And here's my favorite review paper, if you're interested in that. And in the past, since I don't know, the mid-90s, there's been understanding of PDEs in terms of time averaging and fast and slow. These are the original papers I was looking at, but there have been improvements on Choquette's work by these guys too. And this is going to turn out to be important for constructing different ways of approximating the shallow water equations between the GPU and the CPU. So I'm now going to give you two examples. I'm going to give you an example of the heterogeneous multiscale method, which was one of the things we're beginning with. And I'm going to give you an example that follows on of the Choquette time averaging for PDEs in this form. So this is just an ODE, but this is one of the standard examples where G and F are periodic. So this winds up being quasi-periodic, and this has been studied to death. So the fast variable is phi, and the slow variable is I, and you can split these up really nicely, and you can get an effective equation for I by taking an average over phi, which phi is fast. And remember, this is just an ODE. I'm just giving you an example of what the algorithm looks like. So here's an HMM style algorithm for this. You advance the slow variable and you replace G, which would normally contain fast variables, with something that's smoother. But it's not just something that's smoother, it is constructed by the fast model. So it's almost like you're giving a different forcing function to the time advancement, but it's not a stupid process. It's actually using the thing that you've called fast to decide what it is. And this is where splitting it into the actual fast part, which is the linear dynamics, and everything else is useful, because then you know something about how to construct this. So this G tilde, right, is estimated from the microscale model. So you can see that you advance phi, which is the fast variable, in a way we understand, which is holding the slow variable fixed. And this, in fact, gets to your question, is that when you're advancing the fast part, you hold the slow part fixed. This means the boundary conditions can be the same. This means you can use parallel in time on the linear piece. Yes, I saw your eyebrows go up. Yeah, right. And we're exploring that. There has to be problems. There has to be problems.
So just a comment. The
Sure.
split explicit algorithm does, so the traditional method does this. And
Yes.
And it communicates like crazy.
Yes, so split explicit is not breaking things into fast and slow. It's breaking things into the barotropic part, which has fast and slow, and the baroclinic part, which in fact has fast and slow. And the linear dynamics is the fast part. So the split explicit scheme we use does not actually break the problem. It's that the barotropic part is faster than the baroclinic part, but we haven't actually picked out the fast dynamics of the barotropic part.
We've done it well enough that it's stable.
Well, hopefully, Todd, you know, the reason for doing this, well, and also, this is just one HMM style algorithm. But the reason for doing this is not to just replace split explicit. It's to try to make use of these new architectures by splitting it into things we can solve in different ways.
Oh, no, absolutely. I'm just saying that the slow, the definition of slow and fast can be different, but you know, in the split explicit, we hold what we call the slow constant. We pass the average of the fast back.
Absolutely.
Using
Absolutely.
a set of k weights.
Absolutely, absolutely. This is the simplest example of HMM, and I picked it because it's related to what we understand for split explicit. But so for example, one of the things we're thinking of is that this G tilde, which you can see here is an average, that we throw away things like finite volume and spectral element and everything, and we solve all the linear dynamics with particle dynamics. And we have a construction of this G tilde based on a force constructed by approximations of particle dynamics, for example. So I picked this example so that it would connect to what we understand about split explicit, but I wanted you to see where the thing is that we would be making an approximation, right? Which would be in the construction of this G tilde from however we choose to solve the fast or linear part of the system.
So would it be misleading if we were to say the fast part would be something like the non-rotating shallow water waves, gravity waves, and the slow part is everything else, the rotation and the Mosby wave? Is that too physical an interpretation?
No, I think it's one interpretation. I think
because that's where I'm stuck on the communication issue, because the fast waves propagate across your boundaries.
Yeah.
And that's the bit I'm stuck on. That's where I'm having trouble seeing why it doesn't communicate.
so. It will have to communicate, just like everything. You know, when the computer scientists say to me, "You have to make your algorithm asynchronous," I say to them in reply, "I need everything to finish at the end of a time step, and I'm not going anywhere until it's all finished. I'm not advancing anything," right? So at the end of the day, everything has to communicate, right? So how that communication works, I mean, sort of I'm working on this, you know, with Phil and Terry and so forth. So I have to say that there's going to be two strategies. There's going to be one strategy for this case that we have now, which is with this bus. There's this bus that you have to, the two. But in 5 years, they say, they're going to have shared memory, and it's going to be different then. So how we use the data on the GPU and CPU will change. And so I don't know how that's going to go. You know, Terry, when he gives his talk on the last day of PDs on the sphere, will tell you what we know right now. But we're sticking, so, you know, our plan is to look at just a Fourier decomposition horizontally so we know which space all the horizontal stuff lives in. And then we're going to use Mark Taylor has a shallow water code that's doubly periodic but parallelized. So then we'll, with domain decomposition. And then probably his shallow water equations on the sphere. So we'll be getting experience with this, but we don't know. And I'm not trying to tell you I know the answer. I'm trying to show you what I'm trying to, I'm trying to think of a way, and I encourage you all to think of some other way, so improve on what I've shown you. Right, so now I'm going to give you an example of a Choquette-style averaging, where I've now called tau the fast variable, but basically instead of, this is similar to the HMM method that I've just shown you. Here's the advancement of the linear piece, but here we replaced W with a W bar, and W bar has been averaged over the fast time scale. And there are difficulties with this in terms of near resonances, how to advance the problem without doing the near resonances incorrectly, which is why we're sticking to a Fourier code right now, because we can compute exactly what they are in Fourier to see if we're getting it. But these other advances in understanding how to time average the PDE seem to get us over that, and Terry will be talking about the details of that too. And so here's my last slide, which is an advertisement for Terry's talk and what we know about all this so far. But like I said, I don't have the answers. I would be happy to have discussions with any of you about the problem with these architectures, what is known to work well on them, how can we change things, if at all, to take advantage of them so they don't turn into just, massively Monte Carlo methods, and so that we can take advantage of them for our problems. So that's all. Mark?
Going back to this communication thing,
Yeah.
were you saying that maybe you're talking about two different types of communication. The slow piece doesn't communicate with the fast piece. When you solve the fast component, there's no communication with the slow component, which you left on. But the fast component itself has a lot of, maybe using domain decomposition with a lot of communication on how it's solved.
Yes, it could. That's right. And so, but this is part of this is part of the root of what I'm trying to get at with heterogeneous numerical methods. I'm trying to use something like Monte Carlo, Monte Carlo for the linear part. People have studied how particle methods interact with other methods.
It's fair to say split, semi-implicit is an example of such as, it's a special case of such as.
Oh, sure.
It has those same properties.
Yes. Yeah.
You solve a semi-implicit 2D problem independent of everything else.
Yeah.
And that could be solved in one piece of memory and one processor.
Yeah. So the problem with that is it really isn't splitting things into fast and slow. The shallow water equations, the fast dynamics, the shallow water equation supports slow and fast dynamics. There are slow barotropic dynamics that are happening throughout the ocean. And we are only...
So if you get a better splitting between fast and slow, that's an efficiency. That means the slow part can take an even larger time step.
Yes, so this is right. I'm trying to concoct some ideas to do things more efficiently. That's right. That's right. And I don't know how it's going to turn out. David?
So way back at the beginning when you said that Moore's law is ending or has ended, what do you mean by that? Because I actually think it's explicitly not true.
Well, I think you know more about this than me.
Single processor.
So Moore's law says you get twice as many transistors per chip area roughly every 2 years. As far as I'm aware, the current assumption is that we have several doublings of that still to go.
So I think we do have several doublings still left to go, but right now there's all kinds of research going on, and it's the Monte Carlo people who are most interesting.
But so what has changed is that 7 years ago, clock speed stopped going up. We still get twice as many processors, and that basically just means we get twice as many cores. They still go as fast as they did 7 years ago.
They have slowed down, otherwise they start melting. They're actually getting slower.
I agree that. I do agree that they're getting slower, but it's the same. It's the same problem. It's not more. It's not more that's killing us.
It's the power.
It's the power envelope.
Yeah.
But I also disagree.
Right. I agree. I mean, the main point I wanted to make in the beginning was the reason we should take it seriously is the power.
Mm-hmm.
It's the power. Yeah.
I also disagree with you about the programming model thing, but I'm going to talk about programming models next week, so I'm not going to go into...
So you're in the other camp. Yeah.
You shed some old light on that. At the start of computing, there was a specialized processor all the time for our and we had, at the start of the vector computer, there was a competition between FPUs and
Right.
computational FPUs, CPU,
Right.
and this is only coming back. So
It is only
there
coming
may be a
back,
lot
that's
of
right.
algorithm already thought of that I've seen somewhere. I'm speaking after your graduates, your postdoc on the last FPUs here.
Yeah.
So,
Yeah, but I'm not saying, we're trying something. We're trying something to see if it works, but what I'm doing is inviting everyone else to try something a little different than what you know to try to address this. You don't have to do it my way. I don't even know if it's going to work. Yeah. You more?
Frank's hanging out there.
For me, I'll wait. Don't worry.
This sounds similar to existing large codes have been ported to GPUs by just putting a solver on the GPU. And this sounds similar, but you're doing it with split explicitly. It's the same split between the CPU and the GPU. And there's a lot of communications involved in the solver on the GPU. And it does run very well, but it takes the time getting it back.
That's right. That's right. So there's two steps here in terms of the parallelization and the communication, which is what we have now, which has this bus, and the expectation that we'll have shared memory. Right? So I think when we go forward, we have to think of those two things. You know.
Someone remind me, is there inter-thread communication costs within the GPU? There is, but that's
I think so. I
there
think
is a
so.
cost.
I think so, but
It
I don't know.
depends what
Ask
they-
David.
It depends what level you do that. So you have what is called a block that they've had up there, and they so a GPU is actually a whole load of little parallel processors, and within one of those parallel processors, you have communication essentially for free. Between those processors, direct communication is impossible. But you can, if you watch your shared memory semantics, communicate via variables that are in the GPU's global memory, so the 6 gig of global memory you've got. But you've got to remember that 6 gig of global memory is about 400 processor cycles away. So it really hurts. So you really, really, really want to keep your communication within one of these thread blocks. But within them, it's pretty much free.
Frank.
Thank you. So I like your point about we should be actively engaged in having the NVIDIA or the hardware people involved with this, right? But my question to you is, and you talked about it at the end, you said, and this is part one of your talk,
Yeah.
that we shouldn't leave it up to the gamers.
Yeah.
But the problem is they drive the market.
Yeah.
So that's the question is, I can see us, for example, there's some manufacturers like Intel who are probably more willing to work with scientists than I would say NVIDIA, I'm guessing, right?
So
But
the only
can we-
guys I know are the NVIDIA guys, and they were very interested. You know,
But why?
like you
What-
had to explain to them, why would you want double precision? They're like, why would you want? And then they showed me the filter they had. They're like, look, you can have this filter for free. And I said, well, I don't want that filter, right? Because that filter, it's a very simple filter, and they care nothing about what's happening at the boundaries.
Yeah, I'm just curious
So-
because they're not producing any, I mean, the reason why I say Intel is more interested because they have been involved in compilers and other things, right? So they obviously already know that there's a market for them. For NVIDIA, besides CUDA, they really have done nothing else. So
So-
why would they be interested in
Well,
working?
So
No,
you have
they're
hardware for science.
building a big
So-
machine in Tokyo.
But it's not even just that. NVIDIA have sort of come to the party because, like when you run a Tesla card, which is the things that the 2050, the things you put in supercomputers, that is a card which is there for compute, not for gaming. Now, it is not a compute-only architecture. If we got to tell them how to write an architecture, we wouldn't ask for that. But what it is a pretty significant tweak from the game architecture. So it has twice as many double precision units. It has error correcting memory because we care about the answer and they don't. And it has various other changes. So we're not important enough to have our own architecture. We are important enough to have our own variations in architecture. But then I think we then means science as a whole. And I think that's exactly right. We have to make sure that the climate community and more generally the mesh-based community have our vote in what sways NVIDIA.
Yes. Yes, and it's not going to be them coming to us because they don't know. I mean, the NVIDIA people that I've spoken to seem interested. I think actually they're interested in high performance computing, the people. You know, for the same reason computer people have always been interested in high performance computing. So they're interested, but they don't know what to ask. You know, like that, the NVIDIA guy didn't know that I had such a high disapproval of the filter that he had. I was like, well, can you give me a hardware operation for a different filter? And he's like, yes. You know, that's the Mr. Potato Head thing where you change out the nose or something, right? So yes, that is exactly my point. And so we sort of have to be the ones to be a little more active.
Yeah, back to the ENIAC, where you would see the logic gates that are implied with your computation and connect it.
Yeah, it's back to that. Lauren?
Yeah, I'm a bit, I was in this business for quite a while as well, and I saw my algorithms that were designed for certain architectures becoming obsolete at the time actually when I was finished designing the algorithm, the computer was gone. So I got really tired of doing this kind of business, and I don't think that it really serves us well, because it also goes in loops. We had vector computers, so all the machinery was kind of designed for vector computers. Then people came up with these massively parallel machines. Everybody changed, and that was the time when actually Hitachi and these machines were so successful, because all the machinery now was done for the vector computers.
Right.
Now we have our machines, our codes ready for massively parallel, but now we see that vector computers become more fashionable again, which means that in 5 years our algorithms that we are designing now will be obsolete again. And we try to find new ways. So I don't think that we should think actually in these architectures. I think we should strive for finding the invariance in that.
So I'm actually in agreement with you, but this all the locality of the method, I don't think we're doing good enough now.
That's true.
To help them.
Yeah, but
we're not doing well enough with the algorithms to help them or people who are making programming models.
No, but our thinking is still very much in terms of physical behavior and in terms of the physical layout of a certain process. And so we throw it on a grid which is still physically induced. And I think that's the wrong thinking. We need to think in data structures, and we need to start talking to the computational scientists and to the software engineers in terms of what are the building blocks of an algorithm that can be localized, for example. So what are the processes that we can determine that are local, and how can we make sure that we communicate that the global character of our computations is only used in certain, only very rarely, as you did in your time-stepping scheme.
Yeah.
But I think that the whole paradigm needs to be different in terms of wording as well for us in our thinking.
So this is the kind of discussion. This is the kind of discussion we need to have. That I mean, I'm with you. I've just shown you what I know and what I'm thinking, but it's everything. You're right. Everything is changing. But what I understand and what I'm seeing is that people who already have, really super stupid parallel algorithms are gaining the interest of the computing community. And if we engage them, and if we think about how to make our algorithms, whether it's the data structure or the underpinning algorithm, this will help us have architectures that we can use and that we can scale up as time goes on. Because whether or not it's a GPU or some combination of these low power processors and GPUs, and even they're making architectures now with GPUs and GPUs, which means very lightweight operating system. I agree with you. We can't run after that, but we have to start thinking, what can we do to make things even more local than before?
I agree, but we shouldn't look at the Monte Carlo people,
Because that is really stupid.
No.
They can solve all kinds of problems, but But it is a very brute
Well, it's
force
not
human
me
approach.
who's looking at the Monte Carlo people. What I see is the computing community, because they've been able to do it so easily.
Well, that's true, but we're looking to solve real problems and not stupid problems. So we should actually.
I'll
there
let you be the spokesman for us.
Well, you can't get away from the physical nature of the problem.
That's true.
It's hyperbolic. Information travels quickly.
Mhm.
So what we want, we can't have. What we want is fast access to all the memory.
Well,
That's,
So I'm not sure
can I
that's
just-
true.
Can I just,
well,
memory.
no, I'm saying that's what we want and that's what we can't have.
so, well, what, stop.
So that's true.
If the GPUs were basically designed for rendering images in games, and the way they do that is they actually do a ray tracing exercise, and basically, a little block of the screen, you've got so many pixels by so many pixels that you're trying to, each pixel has to be rendered, and that pixel is the sum of several rays, and those rays can actually have information coming from anywhere in the domain because of reflections, and they actually take them into account. So their idea was that yes, they want to have the ability to, the way they look at it is that basically everyone has access to all the data, but the calculations become very localized because you're only doing with the data you need. And I think part of what's being said here is there are alternative approaches. For example, I was wondering if maybe a PIC-like approach to doing fluid dynamics would work here, because you have very
Exactly,
localized
Alistair.
particle interactions. There are other ways to solve something which is still physical. We're so used to thinking about meshes, which is where and communicating across that, and the equations become very non-local in that way. There are, I think, possible avenues which have analogues to ray tracing.
Absolutely, yeah. But if information travels quickly, you still need to communicate that. I mean, that's
but the point was about my analogy for ray tracing is that the data is global, but it's one way. There's not a communication between the rays. That's the key.
So
there was some
this is
approach
what I
where
was.
we can propagate information in a state in only one direction.
This is what I was meaning when I was saying it was possible. Could it be possible that we can construct our own algorithms where we don't have to sync everything? We've designed the ray tracing, the characteristics, so that when we deploy the data, it's all finishing like that,
If GPUs can do ray tracing, could they do semi-Lagrangian?
So,
Which we know works really well.
There is.
You also
And
really
you have to communicate with ray tracing.
Particle methods are very, very easily implementable there. But then the problem is you don't have global quantities anymore. And to some extent that is nice and it produces nice pictures, but it doesn't give you any quantitative information. That's the problem.
you also don't want to use the
algorithm
hardware
does
which is there for doing the ray tracing, which is what Beth highlighted. Because that really is highly specialized hardware and you get the wrong answer. It's just the,
but we could ask for them design.
maybe. I'm not convinced that, I think we should not get hung up on the GPU analogy with graphics, right? I think the important thing is the card that Beth showed at the beginning, which is the cost of various sorts of communication. Because those things are close to invariant, right? The hardware people are attacking those problems, but no one thinks they're easy. So the question you have to ask yourself is, how do I write an algorithm which minimizes those data transfers which look expensive on that chart? And that's kind of a deeper level of understanding the cost function than trying to think by analogy with a particular GPU. Because I mean, hey, Intel Mike's coming out now, and that's not based on a GPU, but it has pretty much those same cost structures, because those cost structures are in the silicon.
I have a comment on Bjorn's comment. Next week there will be a meeting on stochastic PDEs. And I won't make any analogy with what the physical translation do to...
You guys don't have to get my permission to speak. This is a discussion. I mean.
But another historical remark is that in the past, going from single CPUs, low memory, disk access, and changing the model, that if the change were happening often enough with a certain time, you could think of how to morph your code or your algorithm to match this architecture. And I remember, contrary to what somebody said yesterday or 2 days ago, semi-Lagrangian was not designed for the computer, for the vector computer. Actually, when the vector computer appeared, people said, oh, well, first, semi-implicit is never going to float, semi-Lagrangian is never going to float, and so on. So we can find ways, and sometimes things that are completely different from the original thinking. If you just go look around and find a trick that allows you to get the performance out of the CPU that has a certain architecture. So maybe the GPU, this type of architecture is a revolution. So we won't be able to morph things, but to have some, let's say, well, let's do something very differently for one part.
For something, yeah.
Something
You know,
has to give.
We're running out of time here. I propose that maybe we should have a discussion period about this soon. How many of you are interested? I know David is. Well, I'll set something up.